For the talk itself, this is Mr. Larry Hastings, a Python core contributor, PSF member.
Release manager for Python.
Release manager for 3.4.
Yep.
So this guy's going to be spending a lot of time on things we care about, and we appreciate it very much. So with no further ado, Mr. Larry Hastings.
All right, ladies and gentlemen, boys and girls, children of all ages, it's time for the all singing, all dancing Python bytecode. And for the record, if you're watching this on a stream because you are in some other talk, I absolutely forgive you. I would be in Raymond's talk right now if I wasn't here. So, this is an intermediate talk. The goal here is to talk about Python, so you don't need to understand C or any other languages in order to get this. This talk is about C Python specifically because bytecode is an implementation detail of the language. So Python, when you type Python into your interpreter prompt, what you're running is, we call it C Python because it's the Python written in C. Specifically, I'm talking about C Python 3.3 because that's the current version. And this talk will be 100% in Python. There won't be any C on any of the slides. Now, this information I'm going to give you is roughly applicable to other implementations, but not directly. PyPy has its own bytecode, which is similar, but not exactly the same. And IronPython and Jython, the whole purpose of those is that they're using the Java native virtual machine and the CLR, and those have their own bytecodes, and they're very different. But the concepts are going to be relevant, but unfortunately the concepts are only going to get you so far in those environments. So this is really for people who are using C Python. Now, what is bytecode? The best way to describe this is that bytecode is a series of instructions for a virtual machine. The Intel x86 has its own assembly language. Bytecode is the assembly language of Python's virtual machine or of a virtual machine. And let me explain what a virtual machine is because we're going to spend a lot of time there. I wind up saying this in every talk I give. A virtual machine, that's one of those apt analogies in computer science, of which we have very few. It is both virtual and a machine. It is virtual in the sense that it doesn't really exist. It's just software. It's not something you could go over and kick. And it is a machine, and by that we mean it's a computer. So it has registers, and it has a stack, and it has opcodes, or bytecodes. Now, there are roughly 4 different kinds of opcodes I'm characterizing in the Python virtual machine. There's stack manipulation. There's a data stack that I'll talk about in a minute. And so you add things to the stack or remove things from the stack. There is flow control, things like jumping forward. That's instructions that allow you to manipulate the instruction pointer. There are various arithmetic operations. And then there's a whole ton of things that are specific to the Python implementation. Things like creating a set or creating a tuple or loading a closure. Now, when is bytecode used by the Python runtime? The answer is all the time. Anytime that you're running code inside of the Python interpreter, you are running bytecode, which means that there is everything that is expressible in Python is translatable into bytecode. Bytecode, the list of things that you can do in bytecode is a superset of what you can do in Python because there are concepts that you can express in bytecode that you can't implement in C, in Python itself. Like for instance, you can jump forward by an arbitrary amount. You could actually jump backwards from an if statement. You don't have a go-to statement at all in Python, and that's probably for the best. Now here we are 4.5 minutes in, and it's time to ask the question, why bother studying bytecode in the first place? I hope all of you have an answer for that. I have an answer, which is if you're going to be a core contributor and you're going to hack on the interpreter, obviously it would be helpful if you understood how the interpreter worked. I'm a slide ahead. I'll talk about that in a second. But right now I want to say, why have bytecode in the first place? And the answer is that helps you manage the complexity of implementing an interpreter. It's hard enough writing something like Python. In order to manage the complexity of how it works internally, it's best to take an instruction like A equals B and break it into little pieces. And this is a metaphor that everybody uses when they write an interpreter. So Ruby has its own bytecodes. PHP has its own bytecodes, although they're crazy. Seriously. So why study bytecode? Like I said, if you're going to be a core contributor, it's very helpful to understand the implementation of Python. But that's only one part of Python, and there's a lot you can work on even there where you wouldn't have to understand bytecode. So really, I don't think that there is actually all that good reason to understand bytecode, so I'm really wasting your time. Now, there are three reasons that people cite for why you might want to examine bytecode, and I'm not sure that any of them are all that compelling. The more frequently cited is, so you can understand what's really going on inside of Python. And that's true to a certain extent. In order to understand how Python works, you really need to understand how bytecode works. My question is, where do you stop? Because in order to understand bytecode, you really have to understand C. And to understand C, you really should understand assembler. And to understand assembler, you kind of need to understand the microcode on your CPU. And to understand microcode, you need to understand transistors and semiconductors. And to understand those, you need to understand physics and electricity and quantum mechanics. And I will assure you, ladies and gentlemen, that you can live your entire life and be a very productive Python programmer until the end of your days and never understand quantum mechanics. So I don't think that's all that compelling. Now, another reason that people cite is that you can hand tune your own code. You could write your own assembler, which I've actually done. We'll talk about that in a minute. And you could write your own Python functions in hand-tuned assembler and make it just that much more faster. And this is one of those micro-optimizations that I find dissatisfying. You're better off spending time fixing your algorithms rather than hand-tuning bytecode. Plus, bytecode is a little fragile. There are no guarantees about bytecode from version to version because it's an implementation detail. That said, it doesn't change dramatically from version to version very much. In general, if you have bytecode for 3.x, it'll probably still continue to run unchanged for 3.x plus 1. But that's not guaranteed. Finally, and this is probably the most reasonable if you're not going to be a core developer. If you're a pure Python developer, one reason to understand bytecode, because this is the granularity at which the Python interpreter will switch between threads. This is the granularity of the GIL. So if you have a statement like a equals 3 plus 4, that breaks down into a couple of bytecode instructions, which you'll actually see in a minute. And the GIL could jump to another thread between any of them. It'll never switch in the middle of an opcode. So, in order to talk about bytecode, we need to have a sample. Here is my sample. It's a dumb little function called gunk. It doesn't do anything useful. It just illustrates some things about bytecode that I wanted to talk about. So I'll walk you through it real quick. We have a positional parameter called a with a default of 1. We have a parameter called args, which is the variable argument array of positional arguments. And we have a keyword-only argument called b with a default of 3. We print out args. We have a local variable called c we're assigning to none. And then we return a stupid little tuple of a plus b, comma c. Now, the traditional way, if you want to talk about bytecode, you're going to talk about the dis module. And here is the output of dis looking at gunk. Now, I don't want to talk about this in all that much detail. I'm going to walk you through the stuff from a very high level. So this leftmost column, 234, that is the line number that the bytecode came from. The second column, 036910, that is the bytecode offset where this bytecode instruction lives. So for instance, load global lives at 0 and load fast lives at 3. That means that we're seeing two different sizes of opcodes. Some of them are 3 bytes and some of them are 1 byte. The next column is an argument to the opcode if it takes one, and that's why some are 3 and some are 1. Opcodes that take an argument take a 2-byte argument that is turned into a 16-bit number. That the meaning of that number is context dependent on the instruction itself. And some of them don't take that, and the ones that don't take it are only 1 byte long. The meaning of the number, it's totally baffling looking at dis. Load global takes a 0 and that turns into print somehow. How does it work? Well, dis doesn't show you. Another thing I don't like about the dis output is that, I'll remind you, A took a default of 3, B took a default of 1. We don't see those defaults anywhere on the screen. A is a positional parameter, B was a keyword-only parameter, args was the variable argument array, and C is a local variable. All of those are very different constructs, but we can't tell the difference between them on the screen here. We have no idea what say A is versus C is. So I really don't like this, which is what motivated me to write my own assembler and disassembler. Again, we're going to get to it about 3/4 of the way through. So I want to talk about the whole picture, because again, this is only showing you a small slice of it. It's really just showing you the bytecodes and giving you a hint to what the bytecodes, the data that the bytecodes are referencing. But there are really 3 things that you need to understand in order to understand the whole picture and understand how bytecode works and what it's doing. Those 3 things are, of course, the opcodes themselves. You need to understand the runtime environment, the virtual machine in which opcodes run. And you need to understand the data and metadata that is associated with a callable object, with the bytecode and all the rest of it, in order to make sense of what the bytecodes are representing. So I'm going to walk you through all of that. We're going to start with the opcodes. There are 101 opcodes in Python 3.3, and I only have 45 minutes, and I already have so much stuff I want to talk about, I'm not going to get to them. So we're going to talk incidentally about some of the opcodes, and I'll give you some resources where you can research how what the opcodes are and what they represent and what they do, but I'm not going to go exhaustively through the opcodes. It's just not going to happen. But I can tell you about opcodes in general. Like I said, the opcode itself is a byte, and the argument to an opcode is 2 bytes, and it's optional. How do you tell whether you have an optional argument or not? You look at the number of the opcode itself. There is this magical value, you can get it from the dis module, it's called have argument. If the opcode number is less than that number, it does not have an argument, it does not have an oparg. And if it is equal to or greater than that number, it does. So in other words, the size of an in total is 1 if its opcode is less than 90, and it is 3 if it is 90 or greater. With that, let's talk about the virtual machine, the runtime environment of bytecodes. There are really only 3 things, only 3 pieces of data that are associated with a running VM as it's running. There is the instruction pointer itself. You can manipulate that through jump instructions. And that indicates how far along, what offset we are at inside of the bytecode. There is the stack, which is where we put data that we're going to be manipulating. There are some instructions that deal specifically with the stack, like loads and stores. There's also things to rearrange the things on the stack, like dupe and swap, or I think it's called rot2. There's some rot instructions, that's short for rotate. And finally, there is what I call the fast locals array. This is an array, it's just an array that stores Python values, and the fast locals array is used for fast access to local variables, which are things like C, that was defined in gunk, but it's also arguments. Arguments live in the fast locals array. And you access fast locals specifically through load fast and store fast, and the oparg just is an index into that array. So I want to show you real quickly with some cute slides and a little bit of like lame LibreOffice animation. This is what the stack looks like when you're operating on it. So we have a load instruction, and let's say that we have a stack and it contains 2 things. So the Python stack can contain, you can push any arbitrary Python object onto it. So our stack here has a tuple, and above that is a callable object that represents print. And we're going to call load something or other, and we're loading the value of 3. So that boom just appears on top. Now the stack has 3 things, the top thing is 3. The equivalent, the symmetric instruction is called store. The store takes the top thing off the stack and puts it somewhere. And so if we had the same stack and we called store something or other, then we're going to take that 3 and put it somewhere. Now the stack only has 2 things. A slightly less uninteresting example would be binary add. Binary add expects 2 things on the stack. They just need to be things that are addable together. They could be integers, they could be floats, they could be 2 strings. We're going to call dunder add inside. You understand how that works. So binary add, the instruction, takes no arguments, and it's going to pop the top 2 things off the stack, compute their result, push the result back onto the stack, in this case 29. So this slide unfortunately broke right at the last second. I wanted these things to fade in cleverly. Sorry, you get to look at everything all at once. So these are the 6 different kinds of variables that you can load and store inside of Python as bytecodes. Some of them are quite familiar to you, and some of them are a little bit less familiar. But you're familiar with the mechanisms involved. So global variables and built-ins, you load and store using load global and store global. And the oparg, these all take opargs. The load global oparg is an index into what's called a names array, which is just an array of strings. Fast locals, I already talked about a little. That's load fast and store fast, and those go in and out of just a list. And it's literally a Python list. Locals, I'm going to call slow locals. This is the original mechanism used for local variables inside of a function. It's still used as the mechanism for variables stored and loaded inside of a class, inside of a module, and if you're using eval. And you load and store there using load name and store name. The oparg for load name and store name is also an index into the names array, which we'll see in a minute. Consts, load const is an index. Oparg is an index into a const array. And these are just Python values that are pushed directly onto the stack. There is no store const, otherwise they wouldn't be const. Attributes of an object you pull out using load adder, and I can't remember. I think that goes into names again. And finally, cell variables, and those use load ref and deref, and I'm going to talk about cells on this next slide here. So there's this concept inside of the bytecode interpreter, inside the Python source tree, called free variables and cell variables. I puzzled over these for a while. I didn't know what the hell they were. Consider the source code in front of you. We have an outer function called foo and variables, local variables inside A and B. And now we have a local function, a nested function called bar. And inside that, we're declaring non-local B. We actually wouldn't have to. It would find it automatically lexically. But I'm calling it non-local specifically to call attention to it. So A is a local variable. We're familiar with that. And that's, again, saved and loaded using store fast and load fast. B is also a local variable, but it's a specific kind of local variable called a cell variable. All cell variables are local variables inside of a function. And a cell variable is a local variable that is referred to in a nested function. Symmetrically, inside of bar, we have another variable. It's actually a different variable called B. And B is a free variable. A free variable in Python means a local variable that is stored in somebody else's scope. We are a nested function. We have to look outside of ourselves to find it. The mechanism for this I don't actually understand, so we're going to see it go by, but I can't talk about it. So instead, let's talk about all of the data and metadata that is associated with Python bytecode. This is all the stuff you need that's stored in two different kinds of objects in order to run Python bytecode, in order to have a callable object that uses Python bytecode. So let's start with, this is all going to be about gunk, our dumb little function. We're going to start with the type of gunk itself. It is of type function type, which the repr says class function. That is a function object, that is a callable object that uses bytecode. And if we look inside of gunk, we see a whole bunch of dunder stuff. The ones that are in bold and large, those are the ones that are specific to function objects, and I wanted to draw attention to them. You don't have to memorize them. I'm going to go through them in detail in a couple of slides. But the one I want to draw attention to is dunder code. Dunder code on a function object is a different thing called a code object. And inside of a code object, there are a whole bunch of more fields. These start with CO underscore, and there are even more of them. And you need both in order to have a callable object using bytecode. This begs the question, why have both in the first place? If you've got both a function object, and every function object points to a code object, why don't you just get rid of the code object and just have the function object? My guess for this was because function objects have a whole bunch of data inside of them that can't be marshaled, and code objects are strictly marshalable. Now, what is marshal? Marshal is a binary serialization format. It's like pickle. It's built into Python, and you probably have never used it because you're not supposed to. What marshal is used for is .pyc files. .pyc files literally contain three network order integers, magic value, the date and timestamp of the py file it was compiled from, and the size of the py file it was compiled from, which is new, by the way, in Python 3.3. And the fourth thing in a pyc file is the code object that has been marshaled. So code objects have to be marshalable. Function objects cannot be marshalable because they contain references to some data that may not be marshalable and may not even be pickleable. It contains all sorts of wild and woolly objects. The closure object, which contain, any of these could contain arbitrary Python objects. I didn't have space, but there's also KW defaults for keyword arguments. But that's not actually the reason why we have functions and code objects. I asked Guido about this the other day, because he's here. And he said this predates having marshal and predates having pyc files. And the reason for it is because of nested functions. Remember our foo and bar. Every time that you run foo, you're going to create a new instance of the function object that represents bar. And if it had all the fields, all of it in once, then that would be a lot more data you'd have to copy and over every time that you ran the function. Having all of it stored in the central object, and you refer to that as many times as you have nested function calls, that's a lot faster and it uses less memory. So, fair enough. So we're going to walk our way through all of the data that's inside of the code object and the function object for gunk. The big one everyone wants to see is the program itself. CO underscore code inside of the code object is the bytecode for the function. And it's terribly unreadable in this format. This is a byte string. I mean, slightly more readable if you print it out as integers. And here we are. We can actually sort of figure out what some of this is. I think 116 is like load fast. And the next 2 bytes are going to be the oparg. And 124, that's the next one. I don't remember what it is, but it's talking about 2, whatever it is. All the numbers that are over 100 here actually are opcodes. The last one, 83, that's return value. The one that's in the middle line, that's dupe top. No, it's pop top. Throw away the top thing on the stack. So it's not terribly readable in this format, but actually it's pretty simple to write a very simple disassembler. This gets you 80% of what this is giving you, and I can fit it on a single page. So we're actually reusing the dis module because it has a couple of symbols that we need. but we're not going to call into it. Disassemble, we pull out the program, the bytecode from the program. I is going to be our instruction pointer. We print out def just to make it pretty, so it's def name of the function, colon. And then we're going to print out the opcodes, one per line. Pull out the opcode from program sub I. If it doesn't have an argument, we don't have an oparg, and I just print an empty string and I go forward by 1. If it has an argument, I pull out the next 2 bytes, I shift left the second one, or them together, that's the oparg, and I go forward by 3 bytes. And the last line is actually doing the printing. Dis.opname is a dict that maps numbers of opcodes to strings that represent those opcodes, and we print out the opcard afterwards. So if I run disassemble on itself, we get that. And that's almost readable. It's not great. Dis is a little bit better. Dis gives you some extra hints like line numbers, and it shows you places that you're going to jump to. But this is 80% of what dis is giving you. So back to all of the stuff inside of the code object and the function object. Relevant to arguments, we have 4 fields. Arg count is the number of positional only arguments. That's A. CO_KW only arg count. That's keyword only argument number. That's B. We only have 1. N locals is the number of fast local variables inside of the function. And there's also an array of their names called var name, so I don't have to remember what 4 maps to, but that's the 3 arguments, A, B, args, and C. The defaults for the function are stored in the function object, again, because we can't serialize them. So gunk defaults is a tuple, and the way that this works is, let's say that we had a function that had 5 positional arguments, and it had 3 of them had defaults, so it'd be the last 3. Gunk defaults for that function would be a tuple of 3 things. So what you're supposed to do is sort of shift it right and map them back that way. If you have keyword arguments that take defaults, that's going to be in KW defaults, and this is a dict. We have B, and that maps to 3. I learned the other day in researching this, you can actually have keyword only arguments that don't take defaults, in which case they are required keyword only arguments, and you have to specify them every time you run the function. You learn something new every day. So the tables I referred to earlier, globals table, the global names and the names of load name and store name, load global and store global, that oparg is an index into this table called CO_names. So you remember a gunk called print, this is how we find it. Load global 0 pulls out that print string, and we take that string and we look it up in the globals. If we don't find it in globals, we look in the built-ins. This string none here, by the way, is useless. It's leftover garbage from the compilation step because we had the symbol none inside of the function, but that number, that entry into the names array will literally never be used. It's just leftover stuff that nobody cleaned up when they were doing the compilation step. CO_const, this is an array, or specifically a tuple of constant values. These are Python literals that can be serialized, that can be marshaled. And the only one we refer to is none, so here it is. There are 2 things associated with line numbers inside of a code object. We need the line numbers. We need to be able to back compute the line numbers in order to print pretty tracebacks. But we don't use it very often, so it's very highly compressed. There are only 2 fields. The first line number, representing the first line in the file where the bytecode started, where the original Python code started. And then something called LNO tab, which is, gives everybody headaches. Again, it's a byte string. It's a table of byte integers. It's a little more readable in this format. The way that it basically works is you start with bytecode offset 0 and first number being first line no. And then you read out pairs of bytes from this, which represent a delta for bytecode, delta for line number. And you keep adding those down the line. There are some rules about the way the numbers are supposed to be formed in LNO tab. It gives everybody a headache. Hopefully you can live your entire life never looking at LNO tab again. We're almost done. This is all of the metadata associated with the function, and it's kind of split between the 2. The globals, this is the module, this is the dict for the module that was defined at the time that the function was defined. So the function carries its own reference to the globals dict around, which is why it can always find its own globals. The name of the module, the name of the file that was active at the time the function was compiled. I typed it into the interactive interpreter, so I got standard in. The name of the function itself. And the flags. This is a bit field integer, and it's very badly documented because, again, this is a really deeply hidden piece of stuff inside of the implementation of Python. I'll talk you through what that 71 means in a minute. Finally, the stack size. Python pre-allocates the stack for each function as it calls it. and this is the maximum depth that the stack will ever reach. So gunk, I'll remind you, gunk had a binary add, so it pushes 2 things on the stack. That's the deepest the stack will ever get, so we have a stack size of 2. And it actually pre-allocates stacks in advance. It has one stack sitting in the function object, so it can just pull that out and use it directly. If you have nested, then it has to allocate fresh ones. But if you only ever call a function once and it's the bottom of its own stack, then Python's a little faster as a result. So finally, there are 4 fields that I'm just going to touch on in this slide. I'm going to move on. Annotations, so the Python 3 parameter annotations and the function annotation itself. Those would live in here if it had any. It doesn't, so it's an empty dict. If gunk was a closure, this would be some significant piece of data. Gunk is not a closure, so this was none. And then we have cell-vars and free-vars. Again, gunk is neither a nested function, nor does it contain any nested functions, so it has neither cell-vars nor free-vars. These are both empty tuples. I think that's the last time no, there's one more time I'll talk about cell-vars and free-vars. So what I find interesting about Python, consider a module. Well, let's start with a function. A function, you say def foo, you have parentheses, you have colon, and now you have code nested in underneath it. Well, a module is much the same thing. You just don't have the def foo in front, but a module is code. Code lives in callable objects. It lives in function objects. So modules are actually function objects at the end of the day. What does that look like? It doesn't look like much. It's just, if this was a module, all of your code would be in the ... there. And then at the end, we're going to return none, because every callable object in Python always returns something. Modules don't return anything interesting, so it just returns none. And it doesn't take any parameters, because modules are not parameterized, not parameterizable. Classes are slightly more interesting. A class, as a callable object, actually takes a parameter. The parameter is called dunder locals. And there's this boilerplate at the top of every class, and at the bottom, again, we return none, because classes don't return anything interesting. The next 4 instructions, there's load fast and store locals. I'm going to talk about those. Load name and store name, and load constant store name, that's setting up dunder module and dunder qual name, which are, again, boilerplate, and those are not interesting. But this load fast store locals, that is puzzling. I didn't know what that meant. Load fast 0, of course, that's going to load the argument, which in this case is dunder locals. And then store locals, what does that do? Well, this is that thing about slow locals versus fast locals. When you're executing the code inside of a class, the slow locals dict is the class dict. And it used to be that classes would just allocate a dict and then fill it out, and then it would return it or stick it somewhere. But in order to support a new thing in Python 3 called dunder prepare, dunder prepare allows you to override the dict that's passed into a class, and you can create your own dict-like object. And I guess you can do all sorts of crazy harebrained things at that point. Anyway, the mechanism that allows dunder prepare to work is that the dict is now passed into the callable class callable object. There's also a little bit of boilerplate when you bind the class, when you, in order to turn that class callable object into a real functioning class. And this will help me talk about callable objects as well. So let's start with, let's ignore build class for the minute, and let's talk about load const make function. So load const is loading a constant off the constants table, right? Well, a code object is actually a constant object, and they're stored in the constants table a lot of times. So now we have on the stack a code object. Code objects are not callable, only function objects are callable. We need to turn it into a function object, and that's what we're going to do. Make function turns a code object into a callable function object, and it only takes 2 parameters, the code object and its name. The argument to make function, it's been quite a day and I've forgotten what the hell it means. I think it's, oh, that's right. It is a bit field telling you how many annotations there are, how many positional arguments take defaults, and how many keyword arguments take defaults. Since a code object for a module doesn't take any of those, doesn't have any defaults or any annotations, that number is 0. So after that make function is done, there is now a function object sitting on the stack waiting to be called. Load build class, what that does is that's another load instruction, and that's loading a global or built-in called dunder build underscore class. That's a function that actually does the magic thing of building a class object out of its callable, its function object and its name. So this call function at the bottom, the oparg for that, for call function, it's another one of these bit fields. The bottom 8 bits are the number of positional parameters. The top 8 bits are the number of keyword parameters. Keyword parameters are passed as 2 things on the stack. The value for the parameter and the name of the value is a string. We don't have any positional parameters, or excuse me, we don't have any keyword parameters anywhere in these slides. So a call function here is just going to reflect the number of positional parameters that are being passed in. That number is 2. There should be 2 things on the stack right now, and there are load const, which is the name, and the result of make function, which is the callable, the function object that is the body of the class. Boy, that's complicated. So I wanted to show you how you could create a function by hand yourself. It's really easy. It only took me 4 lines, but they're 4 lines that you're not going to like. We start with import types, just so that we can get the function object and code object constructors. We create a code object, and boy, that's readable, isn't it? The middle line there, that's the bytecode, and it's a very simple function. I'll show you what that is in a minute in a more symbolic form. But this literally is creating a code object, and it's ready to go. It's legitimate. It really works. I mean, this whole slide, it actually works. We turk that code object into a function object by passing in the code object and the global stick that we want it to bind to. And the result is a callable function. This function is very cleverly called add. It takes 2 parameters, which it adds together using the binary add opcode, and returns the result. So now I'm going to do this again, but I'm going to make it readable, and that's going to take me 3 slides. So we start with importing 3 things: inspect, dis, and types. Inspect gives us some symbols that we need. Types gives us those things that we need for a function object and code object. Dis also gives us some more, the ability to turn strings into opcodes. So op is going to be a dumb little function that just takes a string and turns it into an opcode number. And here's our program right here. We're going to load fast 0, 0. That's going to load fast 0. That's the first argument. The first argument, the first positional argument. Load fast 1, 0. That's going to turn into load fast 1. That's going to load the second positional argument. So now we have 2 things on the stack, the 2 arguments that were passed in. We call binary add, which pops those 2 things off, computes the addition of them, pushes the result. And return value, which pops that value off the stack and returns it from the function. Simple, understandable. It gets a little worse. So arg count is the number of positional arguments. That's 2. We have no keyword arguments, so kw only count is 0. Number of local variables declared inside the body of the function is 0. And then it actually only wants the total of arg count plus kw only arg count plus local count, and that's the total number of locals. And I'm actually lying because there are 2 more possible ones here. If we had a star args or a star star kw args, we'd have to add 1 for each of those. But we don't. Max stack depth, I happen to know that in advance. That's hard to calculate because Python doesn't give you any of the information you need. I had to hand calculate that myself for my assembler. Flags, this is that mysterious flags number that was 71, I think, on gunk. And this one is actually 67. I happen to know that because you see these all day. These 3 flags, inspect co-optimized, inspect co-new locals, inspect co-no free. That's why we need the inspect module. What do those mean? Optimized means that it wasn't unoptimized. That's as best as I could figure out in the source code. What it seemed to indicate was, let me talk about new locals first, actually. New locals means that it's using the fast locals array. That's all it means. Every function declared since 1992 or so has had this turned on, except if your function has inside of it from something import star. That means that it's going to be creating variables dynamically at runtime. We don't know what that list is. And also, if you use the locals parentheses function, we can't optimize either of those. We can't use fast locals at that point. So we use slow locals. And that's what those 2 flags, it seems like both of those 2 flags mean about the same thing, but I'm not sure. Co-no free means this is a function that doesn't use free variables or cell variables, which means that Python gets to skip some calculations inside. It makes it's just an optimization hit. It makes it go a little faster. Now, I was a jerk, so I didn't bother to define names and var names, even though this does actually have some var names in it. But that's just an empty tuple. It runs anyway. Free vars and cell vars are both empty. It's not a nested function, nor does it contain nested functions. The file name I put standard in, again, because I'm a jerk. There probably was a legitimate file name at that point. Name of the function is add. First line number is 1. LNO table, that's empty, again, because I'm a jerk. If the binary add fails, it's not going to have line numbers. Your host. And finally, we're going to create the objects. Code object, we pass in a type code type, and we just pass in all those variables I just created in the right order. And then the rest of the slide is the same as the previous slide. We're going to create the function type, passing in the code object and globals, and we call add, and it works. That's not terribly readable either. So that's why I wrote my own assembler and disassembler. I have finally posted it to the world. It's called Maynard. I will remind you, Maynard was the keeper of the holy hand grenade, the most effective disassembler known to man or beast. Thank you. Maynard contains my disassembler, my assembler, all of the sample code that I've had on the pages here, and something that I'll talk about in a sec that people have been asking me about. So let's see what Maynard looks like when it's decompiling, disassembling gunk. I think this is far more readable, which is what motivated me to do this in the first place. We can see arg A1, that's a positional argument, thank you. That's a positional argument with a default of 1. KW only B3, that's a keyword only argument with a default of 3. We have star args, and that's called args. We have two globals, print and none. This is disassembling that dumb function that was assembled by Python, so the none string is still in globals even though we never use it. And we have a const called, I assign the name automatically, so it's called const underscore none, and it has the value of none. And we have one local variable called c. Now we can say symbolically, load global print, and we know what the hell that means. Load fast args, and we can see we're loading the args parameter. So again, I find this endlessly more readable. The goal eventually with Maynard is to make it round-trippable so that you could take a function, disassemble it, reassemble it, and get the same function back. It's not there yet. For instance, this doesn't have any L&O tab information in it. I probably need to do that. Now here's something that's a little ticklish to consider. It's really interesting to look at those, the body of the function that implements a class. I talked about store locals and load build class and all that. It's hard to see that store locals thing. How do you get your hands on that? Because by the time you've bound the class, you've thrown away that function object, but that function object isn't stored in any place that's particularly accessible. So just to walk you through it real quick, it's pretty easy with Maynard. Let's say that we had a class and we wanted to see the code that implements the body of that class. Just throw it in a function, disassemble the function, and at the top of that disassembly, you're going to see const index 1, see that? We have a code object. Now again, this is another reason why Maynard isn't round-trippable. The thing to do here would be to have recursive disassembly, which would of course solve this whole problem in the first place. But for now, we can see that the code object that implements the body of h is stored at const index 1. That's a big hint for you. You can literally pull it out of the foo object. Foo.dundercode consts 1 is the code object that is implementing h. And you disassemble that and you get to see store locals. So this, as promised, this is another terrible idea of mine. Perth is a fourth interpreter written to the Python VM. It's really a toy. It's absolutely useless. It doesn't work properly for hardly anything. But it does implement integers, float, and string literals. It implements the following words right now. That's the fourth concept of a word. It does not implement recursion, which is my main problem with it because I will not be satisfied until it can run a Fibonacci generator. You don't have a real language until you can do Fibonacci. So by the end of the sprints, this will work, but it doesn't work right now. And by the way, it uses the John Hopkins local syntax. If you look at the fourth source code, it's all in one file. It's not commented. It's terrible code. Oh, let me tell you real quick. So in Python, you know in advance, like you say foo, parenthesis, 1, 2, 3, 4, 5 with commas. You know the name of the function you're going to compile before you even get to the parameters. In fourth is reverse Polish notation, so you would say 5, 4, 3, 2, 1, foo, if you wanted to call foo. And the problem is, like I've shown you, when you're calling a function, the callable object needs to be on the bottom of the stack, and then all the arguments need to be on top of it, and then you call call function, excuse me. This is a problem for me because what if I have 5 things on the stack? The Python virtual machine doesn't have enough stack manipulation stuff to let me get something from the top of the stack, the callable object foo, all the way under, say, 5 arguments. So what I had to do was, well, if you call a function that takes more than 3 arguments, I think, I build a tuple out of those arguments. Now I have 2 things. The tuple, I have the tuple. I push the callable object on top of it. I swap them, and I decompress the tuple in place. So Perth is going to be really good for performance. So I have 5 minutes left, and I think that's going to be enough time to bring this all together. So I'm going to show you a Python VM which itself is written in Python. This Python VM, like I said, you don't have a real programming language until you can run Fibonacci. So here is a definition of Fibonacci that it's really simple and dumb, but my VM can literally run this. Compiled by Python, a real Python object, I can pull all the stuff out of it and execute it exactly like Python does. This takes me 5 slides. I'm going to go pretty fast. Here we go. Def VM takes the callable object and star args. That's the argument array. I pull out 5 things that I need. The code object, the constants table, the names table, that's for globals, the program, that's the bytecode, and the number of local variables for each call. I pull out the globals dict and the built-ins dict. That's how I can look up globals and built-ins. I create an instruction pointer. I create a fast locals array, which is initialized to the arguments followed by the number of fast locals that I have, the local variables, which I set to a special uninitialized value so I can blow up if you don't initialize your stupid local variables like Python does. And I create a stack, and a stack is just going to be a list. I'm going to append to it to push, and I'm going to pop off of it to pop. While true, we're going to pull out the next operand. We're going to increment forward the instruction pointer by 1. And if this is an operand that requires an opcode, we're going to compute the op arg from it. So we're going to pull out program sub 1 and program sub 2, shift and OR them together. We have our opguard, and now we increment the instruction pointer forward by 2. And the rest of this function is all implementing the individual opcodes. So load const does what by now I'm hoping you're expecting it will. We take oparg, we index into the constants array, we push the result. Load fast, we take the oparg, we index into the locals array, we push the result. Load global, we take the oparg, we index into the names array, that's the name we're going to look up. We look it up in the globals dict, and we find it, we push that. Otherwise, we look it up in the built-ins dict, and we push that. If it doesn't find it in either place, this will throw an exception. It's not a very robust interpreter, but it is minimal, and it does work for, it works for that VM, it works for that fib and nothing else. Binary add, we pop the top 2 things off the stack, add them together, push the result. Same thing for subtract, except with a minus instead of a plus. Pop jump if false. This is flow control. We pop the top thing off the stack, and if it is false, then the oparg indicates the absolute position in the bytecode where we should jump to. And that's how if works. If the thing is true, we do this, else we're going to jump and do that, right? This is all one opcode. It's a very complicated one. Conceptually, it's simple, but it's just a lot of code. Compare op pops the top 2 things off the stack. And then the oparg is a special number that indicates what operation we're going to perform. If it's pi LT, then we do less than, and if it's LE, then it's less than or equal to. Else I just didn't handle any others, so I'm very nice and I throw a nice exit. And whatever the result of that was, I append it to the stack, and we're in the home stretch. There are only 2 more operands left. Call function, this handles recursion. Again, I only handle positional arguments in my VM, not keyword arguments. So if the number oparg is greater than 255, there were keyword only arguments, and I just exit. But if there are only positional arguments, I pop off that many arguments, range, and it's whatever that is, list comprehension. So that's our args array. I pop off the callable object itself, and instead of calling it directly, I call it recursively into the VM so that we're always working the VM. And I just pass in our callable and star args. The return code from the VM call is the thing returned by the function that you called, and I just push that on the stack. And the final thing is return value, which literally is the last instruction in our program. I assert that the length of the stack is 1, so you don't have any extra garbage left around. And I return the top thing on the stack, which would be at stack 0. And this really, really works. This is calling it in a loop, 0 through 9, and I call the real fib, and I call VM, my VM, with that fib callable and the parameter of n, and I get the same results every time. Now, if you play with bytecode yourself, there's something you should expect to see a lot, which is a segmentation fault. The Python interpreter makes no guarantees that it's going to be robust in the face of malformed bytecode. It's very good at running the stuff that it generates. It's very easy to crash. It just doesn't check anything at all, and it just blows up all the time. So if you crash like this, now you have to sit and think, okay, what did I do wrong? Finally, resources in case you want to follow up on this stuff. You will want to import dis, inspect, and future. The dis module has documentation for all of the different bytecodes, but it doesn't show you the stack effects. So I think it's not useless, but it's next to useless. It can see useless from here. There's Maynard itself. That top URL is now active. I pushed that from the stage. The bottom one is not active yet, but I've registered the name on PyPI. And finally, if you want to understand what the bytecodes themselves do, the best resource is, of course, the Python source code, because that's the canonical location of it. But if you don't understand C, my pal Ned Batchelder right there has been writing a pure Python VM for a while called byterun, and you can download it there. And that's all I got. Thanks very much.